All right, so I'll start with giving an introduction. So this will be something relaxing, something fun. So today's lecture, and in fact every lecture is going to be divided into two parts. So we have 2 hours for every lecture, but I'm going to divide this into 2 blocks of 50 minutes with a 10-minute break in between. Okay. So this first part here, lecture 1A, is for this first block of 50 minutes, and then I'll have another set of slides for the second part. Okay. So what I'm going to start with is a brief introduction to reinforcement learning. Then we'll get into the logistics of the course, and I'll tell you a bit more about the course website as well. Okay, so before we get into reinforcement learning, let's start with machine learning. So machine learning has become hugely popular in recent years. And part of it is because when you look at how things have evolved with computer, you could see that computer science, in large part, is this idea where you program a computer to achieve some task, and then when you do a bachelor's degree or any other type of degree in computer science, then a large part of what you learn is essentially how to program a computer to achieve a task. But then, even though this has been the paradigm for many years, things are evolving, and there's actually now a new paradigm that's driven by machine learning. And here the idea is that instead of having to explicitly write down instructions for everything that you want to do, now what we do is we simply provide examples to a machine, and then the machine will simply learn based on those examples what to do. And this has led to some really important breakthroughs. So for instance, if we look at computer vision, so here we've got a scene, and now we can get a computer to recognize different objects. But then in order to achieve this, through machine learning, the idea is that now you essentially feed the computer with lots of images. These images are typically labeled with the information that you'd like the computer to learn to be able to do. And then it will eventually learn to extract the right patterns to be able to recognize the objects that it's been trained to recognize. Okay? So this is a big achievement because in comparison to the traditional way of doing things, now programmers don't have to think through a set of rules about how to extract the right information. So instead, just by looking at lots of examples, then the computer will derive what are the rules on its own. And then so this is extremely powerful because now you can get computers that will essentially learn to perform well in some tasks that we as humans and programmers have difficulty to essentially spell out by specifying the precise instructions. So computer vision has been revolutionized by machine learning. And then another example would be in the context of natural language processing. So here, this is a small example where the computer learns to do machine translation. And here the idea is the same thing. We have large corpora of documents that are in 2 languages, and then if you give that as example to the computer, then a computer will learn to discover patterns in order to match the right words, the right expressions, and even the grammar to go from one language to another. And again, if you try to write down some rules, obviously you can do word-for-word translation, but then if you want to get the grammar right, and in many cases words do not translate directly into similar words in another language, then you need to think this through, and then there's been decades of work trying to do machine translation without, by simply coming up with instructions. And it's very difficult. It just doesn't work. It doesn't generalize well. But then through machine learning, we can do this. So in other words, the beauty of machine learning is that now, again, we've got this new paradigm, and we're not just writing instructions. We're now providing examples. And then the tasks that used to be very difficult now can become much easier. At least even people that have no computer programming knowledge can even provide these examples, and then with obviously the right toolkit, they can perform some tasks, or at least train a computer to perform some tasks that traditionally were very difficult. Okay, so this is where we are with machine learning. But then this success is due in large part to what is known as supervised learning. Okay, so here again the idea is that we provide the computer with some examples, and then those examples, they contain what is the correct output, and then the computer simply learns from this what to do. And the bottleneck for doing this is that we need lots of data. Okay, so again, if I go back to the previous example, so here I would need to feed images, but with the labels, and or in the context of natural language processing, I would feed some text with what is the correct output. Okay, so now the question is, what can we do in order to get around this bottleneck? And then what a lot of people are seeing as really promising alternatives include unsupervised learning as well as semi-supervised learning, but also reinforcement learning. And so this course is going to be about reinforcement learning. So unsupervised learning and semi-supervised learning are also quite exciting, although the reality is that these do not work as well in the sense that often if you don't have labeled information, that's what unsupervised learning means, then you can often suffer from concept drift. Whereas with reinforcement learning, we're going to see in a moment that you have some information that is not the correct output, it's not the right label, but it's still information that kind of tells you whether what you've done is in the right direction or not. So it's a reinforcement, so it's a weaker signal, but that signal is often sufficient to drive the learning, drive it in the right direction, so that we don't suffer from concept drift or other issues like this. Okay, so again, yeah, this is a topic of the course, reinforcement learning. Okay, so now you might ask, what is reinforcement learning? So here, it's been called in various ways. In fact, reinforcement learning is the traditional name within artificial intelligence, but then in other fields, like in control as well as operations research, they might use, for instance, optimal control, approximate dynamic programming, and also neurodynamic programming. So these really refer to the same thing. It's just different perspective, maybe a different history. But in any case, for the purpose of the course, we're going to stick with the name reinforcement learning. But when you check out some books or you look up material on the web, you might see these expressions, and it often just refers to the same thing. Okay, Wikipedia also gives us a very nice definition here. So reinforcement learning is an area of machine learning inspired by behavioral psychology, concerned with how software agents ought to take actions in an environment so as to maximize some notion of cumulative reward. And you'll notice here that I've highlighted some words. So here, for reinforcement learning, there's some notion of agent, and then those agents are going to take some actions. Okay, so they take actions, and then when they take those actions, it is in some environment. But when they take those actions, there's a goal, and the goal is going to be to maximize some reward, and there will typically be multiple rewards, so I guess maximize some notion of cumulative reward. So now we're going to see in more details what this means with some concrete examples, and then this should give you a good idea of really what reinforcement learning is all about. Okay, so again, reinforcement learning comes from psychology, behavioral psychology, and in particular, if we look at animal psychology, what's interesting is that we have discovered ways over centuries, if not millennium, to train animals to behave in a certain way. And even though we cannot talk to them directly, we can still provide them with some reinforcements which will induce behaviors that we're hoping to see in those animals. So if you've got a dog, perhaps you've had a bit of this experience, and then often you might use some some negative reinforcement as well as some positive reinforcements. And then depending on the situation, some might be better than others. But the idea is that now we're going to ask, can we do the same thing with a computer, right? Can we drive the learning for a computer, get it to do the right things simply by providing some reinforcements? And here, obviously, we're not going to inflict any pain to any computer, and we're not going to feed our computer with anything, but mathematically, what we're going to do is define some numerical function, a numerical measure, and then we're simply going to tell the computer, now that's what you need to optimize. So there's going to be a utility function that measures how good some situations are, and then we'll simply want the computer to maximize that. Okay, so then we're going to give the computer essentially some points, and then based on that, it will learn. So this is a very simple, very general way of interacting with a computer. And in fact, it's something that anyone can do, right? So you don't have to be a programmer. You don't have to know how to write Java code or Python code or anything like this. And this is also one of the beauty of reinforcement learning, that it really opens up the door. It democratizes machine learning so that at some level anyone could interact with a computer and teach it to do something. Okay, so the framework that we're going to follow can be abstracted as follows. Okay, so here I've got a box where I've got an agent. So if you remember the definition from Wikipedia, we said that there's going to be an agent, and then this agent is going to take some actions or execute some actions. These actions are going to be performed in some environment, and then the result is that based on this, there will be some rewards that the agent will want to maximize. Okay? So the Wikipedia definition was essentially referring to this feedback loop, where what we are essentially doing is we can think of the computer as being the agent. Now, depending on the situation, right, the computer will have different actions that it can execute. So this will be the output of the computer. They will have an effect on the environment, and the idea is that the computer is going to produce some outputs that will hopefully get the environment into some good states. Okay, so the environment here, it can be users, it can be other computers, it can be nature in general, so it really depends on the scenario. We're going to see some examples in a moment. But the idea is that we can characterize the environment by some notion of state. So this will be a description of the status of the environment or the status of the world. And then based on this, then the agent is going to select some actions, observe what the state of the world is, and so on. And then at every step, there will be some feedback in the form of a reward. This is going to be a numerical feedback, and we will simply ask the computer to maximize these rewards. Okay, so basically the goal in reinforcement learning is going to be to figure out a way to choose actions that maximize the rewards. So this is still, well, it's not very precise yet, but we're going to see in the coming lectures how to make this precise. But that's at a high level what this course and what reinforcement learning is going to be about. So essentially, how can we design an agent, so a computer system that will choose actions, ideally the best action possible, to maximize some rewards and therefore accomplish some desired task in some environment. Okay, any questions regarding this? Yes? Okay, so the question is, what does the state mean here? Okay, so yeah, I haven't defined formally what a state is yet, but essentially the state is going to be a description of the environment that's going to be sufficient to infer what is likely going to happen in the future. The reward in some situation can be considered as being part of the state description, or it might be considered as being outside of the state description, depending on whether or not it is useful in terms of predicting what will happen in the future. So typically we distinguish those two, although the reward could be part of the state. But we typically distinguish those two because we're going to use them for different purposes inside the programs that we're going to design. So here the idea is that the agent is, generally speaking, going to be looking at the state to select the next action, and then it will simply look at the reward to see how well it did. Okay? Yeah?
What's the difference if, between the reinforcement learning and supervised? And in this graph, I feel like the other, like supervised and unsupervised, are also kind of the same model here?
Okay, so yeah, the difference with respect to supervised learning is that in supervised learning, what happens is that you would select actions or you would make some decisions, and what you would receive as a result is essentially the correct action. So somebody or the environment itself would simply tell the computer what was the correct thing to do. Here, when I say reward, it's going to be a numerical signal, or at least we're going to see some examples in a moment, where this reward is going to be a weaker signal. It's not going to tell the computer that this was correct or incorrect. The computer is just going to have some notion that, oh, if this signal is high, perhaps this was a good thing, but I don't know if it was the optimal action or not. And if the signal is low, perhaps it means that this was not a good action, and then maybe I should do something else. So this is the first distinction. The second one is that here, although this is not explicit in this slide, but the rewards might be delayed. So normally in supervised learning, when the computer makes a decision, selects an action, then it finds out immediately what is correct, and then it can learn from this, or at least it's given what is the correct thing to do. Whereas in reinforcement learning, imagine that you're playing a game. Often you're going to select some moves, one after the other, and you don't know if those moves are correct. But at the end of the game, you're either going to win or lose, and then if you win, then you can assume that perhaps all of the moves along in the whole sequence were good. But if you lost, then it means that perhaps one of them, or at least one of them, was not so good, right? So this is an example where we might get a reward much later. So here, if it's just win or lose, right, then it's at the end of the game. And then it doesn't tell us immediately what is the correct action. In fact, there's a credit assignment problem about which action really led to a win or a loss. Okay, any other questions? All right, very good. Okay, so let's go through now some concrete examples. So here I put down some list of applications. This is not a complete list, but it illustrates how general the framework is for reinforcement learning. So we've got at the top here game playing. So this is an area where reinforcement learning has been dominating. We're going to see in a moment, in particular, an example with the game of Go. It's also been used, in fact, the very first success of reinforcement learning for games was in the context of backgammon. And then recently as well for video games, to play Atari, then reinforcement learning is surpassing humans in terms of playing various types of video games. Now historically, what was the main area in which reinforcement learning would get applied was operations research. So here there's all kinds of problems with respect to pricing, resource allocation. One example here is vehicle routing that I'll go through in a moment. Another interesting one is elevator scheduling. There's also in robotics various control problem. There was an important success roughly 10 years ago for helicopter control that was developed by Andrewing at Stanford, and I'll show you a video for this as well. Today, spoken dialogue systems have become very popular. So these are essentially conversational agents. We'll see some examples for that too. Reinforcement learning is also used in the context of data centers to optimize their energy consumption. In the context of computer networks, there's now a lot of interest to use reinforcement learning to manage those networks automatically so that the network can essentially auto-diagnose itself and then adjust itself based on how the conditions of the traffic and so on are impacting it. So self-managing networks. Also very exciting are autonomous vehicles. So here, lots of car companies and other companies too are developing various ways of getting vehicles to become fully autonomous, and then various aspects of this are done through reinforcement learning. And then finally, computational finance. So for high-frequency trading, reinforcement learning is often used as well to decide what might be the next trade that should be done based on past data and so on. Okay, so these are, I guess, again, it's an incomplete list, but it's an illustrative list of applications. Now let's go into more details with a few of those. So as I mentioned, operations research was historically one of the earlier domains where reinforcement learning was developed. In fact, at the time, it was called approximate dynamic programming. So that, in fact, that's still how it's called in that field. So here's an example where let's say that we have a vehicle, and then this is a company that might have different warehouses, and then it might have as well different customers, and then there's a vehicle or otherwise several vehicles where we have to plan the route so that they can go from one warehouse to another to perhaps a customer site and so on, and essentially move different widgets. Okay, so here the vehicle routing software would be the agent. Now the environment would be here some notion of demand. So what I mean by demand is the orders that might come in from customers, and then even within the company where there are some warehouses, so there might be needs as well to ship different parts from one location to another. So all of these things, we can call that the demand, and then it varies. We're never certain what's going to come up, and then so we would say that this forms some form of stochastic demand. Now, the state here could be the vehicle location, its capacity, and then the request made by various depots. And then the action could be the route of the vehicle. And then finally, the reward here could be the negative travel cost. So here, in this situation, we don't want to maximize rewards per se, but we would like to minimize cost. So I guess that's why here I put a minus sign. So it would be the negative travel cost. So essentially, you want to find a route that gets the vehicle to visit different sites, and then will carry different widgets, different supplies, either to other warehouses or to customers, and then do this in a way that would be the most efficient. So this is an example where there's been a lot of work for transportation to optimize this, and historically this has been done through various ways for operations research, including approximate dynamic programming, which really corresponds to reinforcement learning. Okay, another example is robotic control. So here we've got a helicopter, and then if anybody has ever driven a helicopter or otherwise played with a small-scale helicopter with a joystick and you try to control it, it's very challenging. Part of it is that the helicopter is naturally unstable, and then so driving it is not an easy task. And then so here, for many years, there's been lots of interest in developing controllers to allow unmanned vehicles to go from location A to location B, or otherwise to follow certain trajectories. So in this case, for the helicopter, we could say that the agent is the controller. The environment would be the helicopter itself. We could also include the air and the atmosphere around it. Now, when we want to talk about the environment and describe it, so here we want to describe the position of the helicopter, its orientation, its velocity, and also angular velocity. Okay, so all of this would determine what matters with respect to the helicopter. And then the actions, so when you're piloting a helicopter, then you would typically activate the collective pitch, the cyclic pitch, the tail rotor control, and then this would get the helicopter to move in various interesting ways. Okay, and now let's say that we want the helicopter to go from one location to another, perhaps following a certain trajectory, right? Then we could say that here the reward would be to minimize, well, I guess normally with reward we maximize, but here I'm going to look at the negative deviation from the desired trajectory. Okay, so I guess there's a trajectory that we'd like the helicopter to follow, and then so as the helicopter follows the action of the controller, then it will perhaps deviate from this trajectory, and we simply want to minimize this deviation. So in other words, maximize the negative deviation from the desired trajectory. Okay, so this problem, there was an important breakthrough. So this was around 2008. So Andrew at Stanford, with his research group, developed a controller that essentially drove a helicopter, and then he entered it into a competition. So this was a competition for acrobatic maneuvers, and then so this was a competition normally among humans who would all have some small helicopters with a joystick, and then they would essentially get their small helicopter to perform certain acrobatic maneuvers. Okay, and then there would be judges who would look at this and score how good those maneuvers are. And then so what he did is that for each maneuver there's essentially a trajectory, right? And then so he got a reinforcement learning agent to essentially follow this trajectory. And then here it learned to follow it very, very well, to the point where the helicopter that was entered was ended up winning the competition. So it was able to accomplish all the maneuvers very well and better than humans. Okay, so let me show you a quick video for this. Okay, so you can see the helicopter that's about to take off. Here we go. And now it's performing some of those maneuvers. Okay, so here's another one, the split S, then the snap roll, stall turn. It can also do some loops. A pirouette, more loops. Okay, so this keeps on going, and basically, when you look at this, I mean, it doesn't look like the helicopter is moving in a way that makes sense, but for experts, you can recognize these maneuvers, and they are quite tricky because, I mean, it's flying in basically every direction, upside down, and so on. But it's all managed as intended, okay? Okay, so the next one I'm going to talk about is game playing. So this is an important topic over the decades where reinforcement learning has been quite successful. And now So the game that we are looking at here is the game of Go. So it is one of the oldest, but at the same time hardest game or board game that humans typically play. So this game is very popular in Asia. So you have two types of stones, white and black. There's white stones for one player, black stones for the other player. And the idea is that at every turn, each player puts down one stone, so they alternate. And then the goal is to essentially surround some territory, where the idea is that all the intersections that are empty and surrounded, let's say, by black, would belong to black in this case, or like in this case here, this territory would belong to white. Okay? So the idea is that you'd like to surround some territory, and then you can also capture some stones. If there's one stone that is completely surrounded by other stones of the other color, then that stone is captured. So that's at a very, very high level. Okay. Now, the rules of the game are very simple. So, I mean, I've pretty much explained the core of the game in a few seconds. So that might feel like it's a very easy game to play, but it is, in fact, one of the most difficult games to play. So here, to play Go, we can design a reinforcement learning agent, and in fact, DeepMind designed such an agent several years ago and got it to become essentially one of the best program to play. And the way to formulate this is that now one player is going to be the agent. In this case, the environment is going to be the opponent. The board configuration, we can think of this as the state because it gives us all the information that matters in order to play the next moves and to make predictions about what might happen in the future. The action is going to be the next stone location. So at every turn, we put down one stone, and essentially the choices are to put a stone down at one of the empty intersections. And then here, one way of formulating this game is that you could say you earn +1 when you win, and then you earn -1 when you lose. Okay? So then there would be a single reward at the very end of the game, indicating whether you win or lose. Okay, so this is the game, and then DeepMind programmed a program called AlphaGo, and then it defeated one of the top players. His name is Lee Sedol from Korea. There were 5 games, and then AlphaGo won 4 of them, and Lee Sedol won 1 of them. Now, Lee Sedol is one of the top players in the world, and this was a major event because up until then, the game was so difficult, and computer programs were often being beaten by good players, but not necessarily professional players. And then so it was seen as a frontier that computers had not breached yet. But then in 2016, this was changed, and then AlphaGo ended up beating this top player. And now something really interesting when, in fact, okay, for this event, if you're interested, there is a documentary that DeepMind published, so it is available on YouTube. It's called AlphaGo, so I encourage everyone to check it out. So it's a very nice documentary that describes the 5 games, what happened, and so on. But then in game 2, AlphaGo made a move. This was the move 37, which was very, very interesting because first of all, the game had been going for some time, and then Lee Sedol decided to take a break, go out for a smoke. And then, I mean, while Lee Sedol went out for a smoke, the computer doesn't know that, so it just keeps on playing. So it made its move 37. But move 37 was very unusual. So the event was being covered by lots of media. There was a team of commentators in Korean as well as in English, and then they had professional players essentially make comments throughout the game about what was happening. And when that move was made, then the commentators were scratching their heads, were like, this is weird, like nobody would do this, okay? And then the first reaction was like, okay, AlphaGo just made a mistake, and this is bad, right? But then, you know, people started thinking, well, what if it's not a mistake? And then Lee Sedol came back from his smoke and then looked at the move, was also scratching his head. Normally he would play within roughly a minute for every move, but then for this one, he took 12 minutes, okay? And then so the question that everyone had, and nobody really knew the answer, probably not even Lee Sedol at the time, was this a mistake or was this a good move? And it turned out that this was a very good move. A move that no human would typically play. So there was an analysis done afterwards, and then the odds that a professional player would play this move was estimated to be 1 in 10,000. Okay, so humans would normally not play this, and that's why when everyone saw this move, everybody was scratching their heads. And then the typical reaction again is that often, you know, we think we're better, and machines, you know, are stupid, right? So the computer must have made a mistake. But in this case, it wasn't. Now, how did the computer come up with a move that humans would not do? So you see, in this game, you can train a computer to play it in various ways. If you're using supervised learning, and in fact, that's how AlphaGo started as well. So you can take some board configurations with the move that a professional player would select. And then you can train the computer to essentially learn to play just by looking at examples of board configurations and then the move, not necessarily the correct move, but at least a very good move that a professional player would make. And then so in that way, through supervised learning, you can get a program to mimic and learn from those professional players. But then the question is, can a computer just with this beat a human player? And can it eventually figure out to select moves that humans would never play? And obviously the answer is you could not do this through supervised learning, or at least it would be very unlikely that a computer could generalize in this fashion just through supervised learning. But with reinforcement learning, this is possible. So the machine there ended up playing lots of games against itself. And then it was learning to refine its moves and so on. And then it eventually discovered that, well, there is a move. In fact, I'm sure there were many other moves like that, where even though humans would not play it, it's a very good move. And then so it learned this, it played it, and then this shocked the world. And at the time, again, nobody understood the significance of move 37 because it wasn't clear whether this would be a good or bad move, but afterwards, based on the analysis, everybody eventually agreed that, yeah, this was a turning point, it was an excellent move. Any questions regarding AlphaGo or Go in general? Okay, let's keep going. Okay, another very exciting example are conversational agents. So here's Siri, where you can ask, when is the Seahawks next game? And then it might answer with the Seahawks battle the Titans for Monday at 6:05, right? So everyone has experienced this. If you've got a smartphone, you can interact with your smartphone, and there's a conversational agent. Now, you can design conversational agents in many ways. Historically, they were designed through a bunch of rules. And these things were more or less hard-coded. Then there's been a lot of use of supervised learning to, for instance, recognize intents. And now the frontier is to use reinforcement learning to essentially get a conversational agent to learn from implicit feedback throughout a conversation. So here we can frame this as a problem in reinforcement learning where the virtual assistant here would be the agent. The user that it converses with is going to be the environment. And then the state would correspond to the history of the entire conversation so far. And then the action would be the next utterance, so the next thing that the virtual assistant would say. And now, in terms of rewards, there's many ways we could define some rewards, but we could imagine having some points based on completing a task, or otherwise perhaps entertaining a user, or ensuring that there's some form of user satisfaction depending on what the task is. Okay, so this is a very general way of framing this, and today it is an active area of research, but this is a great example where, again, the hope is to get computers to be able to learn over time as they interact with users, and not rely just on how they were programmed or what they learned based on some data offline. Any questions regarding conversational agents? Okay, so there's lots of companies that are producing conversational agents. I cannot tell you for sure what each company is doing. What I can say is, in general, historically, conversational agents were essentially rule-based system. Then, at some point, they started using various forms of supervised learning to perhaps recognize intents, recognize specific entities, recognize different interesting things that should be detected as part of what is said here. Okay, but now, yeah, there is some research ongoing in terms of using reinforcement learning to allow the agent to continue to learn beyond just some data that might be provided for training in a supervised fashion. Because again, if we train in a supervised fashion, what we're saying is that we get the computer to essentially just mimic what is in the data, and that means you have to collect lots of data, examples of conversation. This can be a very effective way of getting an initial agent, but if you wanted to keep on evolving, to go beyond that, then this is where reinforcement learning comes into play. I would speculate that this is not used everywhere yet in the industry, but it's getting there. Yeah.
Is the training in a production environment ongoing, or do they usually train the system offline and then put it online and it just does inference?
Yes, very good question. Yeah, so is the training done in production, or is it done offline? And here, I would say in most industrial setting, the training is typically done offline. This is in part why supervised learning has been quite effective and has been embraced a lot. And reinforcement learning is still something that I guess various companies are starting to adopt, because it requires us to think in a different way. So we can do offline reinforcement learning, but where there's real power, something really interesting, is when you can also do it within the production environment in an online fashion. But you can imagine that this causes all kinds of headaches for the production team, because the traditional paradigm is that you have your program, and then you test it, and it's only after all the bugs have been figured out, or at least everything you can think of, that then you deploy, right? But now if you have something that keeps on evolving while being in production, then there's no guarantee that it might not go from a state where it's working fine to a state where now it's making mistakes, right? So this is something that's also ongoing in terms of research. So how can we design effective ways to allow reinforcement learning techniques to be deployed and in fact do this learning within production? Any other questions? Okay. All right, let me give you one last example from computational finance. So in this example, this general example, we could consider an automated trading agent, where the idea is that there might be some securities or some stocks or various things that we might want to trade, and then we would like an agent, which is a trading software, to make the decisions about buying or selling, right? And then the environment here will consist of other traders. And then in terms of making the decisions, then the information that will typically be used would consist of the price history. There might be additional information, like if you're also considering text, you might consider press releases and so on, but at least traditionally, you would consider mostly price history. And then the actions could be at any point in time that you want to buy, that you want to sell, or that you want to hold. And if you buy or sell, there's a question as well about what quantity of stock do you want to buy or sell. And then the reward is simply going to be the amount of profit that you make out of this trading. Okay? So this is very general. Now a concrete example that is definitely being used within financial institutions is this idea that often you might have a very large trade that a customer would like to make. So somebody would like to purchase lots and lots and lots of shares of one stock. And the problem with this is that if there's a large buy order, then everyone will see this and then assume that, ooh, there's a lot of demand. Therefore, let me raise the price at which I will sell. And then if this person really wants to buy so many shares, then presumably this person is desperate. Therefore, we can raise the price, right? So this is how these things would normally occur. And the problem is that this person who wants to buy all those shares obviously would not want to communicate information about the fact that it does want to purchase so many shares and does not want the price to raise just as a consequence of the fact that it's advertising that it wants to purchase lots of shares. So then the problem is, can we buy lots of shares, but let's do it little by little. So we're going to buy small quantities, lots of them, repeatedly. And in this way, it's not going to be so apparent that this person does want to buy lots of shares, and then perhaps the price is not going to increase as much, and then the person can obtain the shares at a reasonable price. Okay, so it is used for this because in this case, it's clear that when we start dividing a large order into smaller orders, we can't manually sit at the desk and then put all of these small orders one after the other. So you'd like to automate this, and then you would like to do this in a way where you will again affect the price as little as possible. Okay, so that's one concrete example, but in general, I mean, there's lots of examples as well in computational finance where this might be used. Any questions? Okay. All right, so what we've seen through those examples is that reinforcement learning is something that's quite comprehensive, but at the same time, it's also challenging. So we've seen that there's lots of scenarios where you can use that, but then what makes it challenging is that in most of those scenarios, the environment is going to be stochastic. So the way the environment is going to evolve as a result of the actions is not going to be deterministic, so we're not going to be entirely sure what the consequences of the actions are. The model that we work with of the environment might be incomplete. Okay, so in many situations, we just don't know really how the environment is going to behave, and then we need to learn about this. So this is where reinforcement learning, we're going to see there's one important topic, which is model-based reinforcement learning in order to learn what is this incomplete model. The decisions or actions that are executed typically are going to be in a sequence, and then they're going to be interdependent. So consider again the game of Go. Every stone you place has an impact on the game, and then will influence what are the other actions that you're going to execute. So this makes it quite difficult because in comparison to supervised learning, where in supervised learning you're given a data point and then you're asked now, let's say, to classify it or to make a prediction based on it, right? Then it's like just a one-shot decision, and then whether you get it right or wrong, it has no impact, presumably, on what you're going to have to do with the next data point. So here, these things are interdependent, so it makes it much more complex. Okay, so there's no supervision, so we've talked about this already. So in general, you see you get a signal that tells you or gives you some information about whether it's good or not, but it doesn't tell you what is the optimal action to execute. And often this signal is going to be partial and also delayed. So again, with the example of the game of Go, so it's only at the end of the game that you either win or lose, and we don't know at any point in time. So like move 37 that we talked about, when it was performed by AlphaGo, nobody was sure. The immediate reaction was like, oh, this must be a mistake. But then after that, people were like really unsure, and then we just needed to see how the game would evolve based on that. So most of the time, it won't be clear the signals that we get. What are they telling us? Is it that the current action, the last action was good, or is it that some earlier action was good? And in this case, for like move 37, then it was really just at the end that we found out that the game was won, and therefore we concluded that, oh, it must be a good move. Okay, so yeah, this makes it really challenging. That's also what makes it really exciting. And in terms of machine learning, so here, what this is going towards is this idea of lifelong machine learning. So classic machine learning, which is often supervised, you have your data set, you learn from this. Once you're done training, you can deploy, make some predictions, right? With reinforcement learning, the learning doesn't stop, right? So what's going to happen is in this feedback loop that we talked about, at any point in time, the agent selects an action, but then will receive some reward from the environment, which allows it to perhaps refine its knowledge, learn further, and perfect future actions. So from that perspective, reinforcement learning provides us with a good framework to do some machine learning that's interactive, that goes on over a long period of time, and that we could call lifelong machine learning. So in the same way that you and I are essentially learning throughout our lives, right? Why can't a computer keep on learning? Because some tasks obviously are going to require learning over a long period of time, as opposed to just, I guess, one time with respect to one data set.